Jerry has been in a leadership position for over 30 years in systems engineering, program management, business development, working for Navy, Army, Defense, and Marine Corps. And his recent job is business director at MACOM, developing actively steered, electrically steered arrays. And today he is going to tell us more about this very innovative and interesting topic. Jerry has earned a Bachelor of Science in Electronic Engineering Technology from Wentworth Institute of Technology. And here's, I give you Jerry.
Great. Thank you. Well, thanks a lot. Appreciate the introduction. To expand a little bit on that introduction, I've been at MACOM since April of 2 years ago, so 2 years now at the company. Before that, I finished my career at Northrop Grumman out of the Baltimore facility, radar facility by the airport. For those who know that, I spent 15 years at Northrop, 14 years previous to that at Lockheed, and 4 years on submarine programs in Groton, Connecticut. So my wife and I were down in DC for 20 plus years and decided it was time to go home after our kids left the nest and moved back up to New England to join the MACOM team. What I was asked to do for this lunch discussion was really talk about the radar roadmap, kind of go through it, not just in the technology sense, but also from the market perspective. In a review a month and a half ago or so, we talked also about, some of you in the room may benefit from a discussion a little bit of the acquisition process that the government goes through as it's acquiring systems. And so I have a couple charts in there. So really the roadmap for this briefing is going to be about 13 charts. I'm going to talk about the operational requirements. That's an area that I lived in a lot when I worked for the Navy and the Army, talking to the warfighters and the requirements people about what's required of a radar system to be built, or any of the command and control systems that I worked on. I'll walk through the specific procurements that are exciting for the community and where a lot of this discussion of microelectronic packaging fits in. And then I'll go through one of the technologies that MACOM uses or has developed and walk you through there about some of the trade studies and how that will relate to packaging of electronics and that type of applications. So we'll get into the application discussion towards the end of the briefing after we go through the higher level overview things. So with that, again, as I said, talk to operational needs. So, if you look at what's going on, you've probably heard of a lot of the UASs that are interrupting airspaces over airports. We had one in the news that flew over Fenway Park a few weeks ago. So a lot of effort on tracking everything that's in the airspace. So when I started in A&D, I was pretty much worried about the Cessna that didn't fly the flight plan that he, put out. Now it's everybody going to buy these drones at stores and flying them in places where they may interrupt air traffic or cause harm if they were to fall on somebody and things like that. And then certainly from the military aspects, there's things like on the upper left bullets there, counter rockets, artillery, and mortar, right? Radars are used for that. That's a big focus. Missile defense type applications. As I mentioned, air traffic control and weather related tracking are all some of the key requirements for sensors ongoing. And in the traditional radar, non-AESA capabilities, what we're seeing is the AESAs are really required to meet all of these missions. So things that have transmit-receive modules, that have digital capabilities at the aperture, that are capable of doing sub-aperture, frequency, agility, wider bands. The government typically had bought in the traditional bands of SC and X bands. Now we're looking at a lot of apertures that have wider band capabilities and things. And then the drivers for the system. So I have some pictures up here, right? If you're forward operating base, that's what FOB stands for. I was also cautioned to, I use acronym soup like a lot of DoD guys do, so I'll try to point some of those out. Forward operating base is a force deploys as a battalion, a platoon. You know, you're familiar with what the Patriot radars are, probably. Sentinel radars, right? Gator, Northrop built Gator radars, right? We deploy those, you know, cart them in on a trailer and that kind of thing. Then you have, you know, facilities like nuclear facilities or other facilities that we're protecting and monitoring the skies. Those are fixed installations, right? Things that can go on towers, whether they be antennas on water towers or the like, very fixed type of things. And then we have all these vehicles, and I put pictures of trucks, but it could be ships, you know, things that maneuver a lot, right? So if you look at the bottom bullets, you know, what really are the constraints for when we're building antennas and systems? You know, it's those physical platform environmental constraints. What you build for a ship is not necessarily what you want to build for a land-based fixed site, or vice versa, right? A land-based fixed site antenna is not going to probably go through the same salt fog testing and things like that that a Navy radar would. So I'm always cautioning our engineering team who go back and leverage a previous system to make sure we really understand the requirements, right? And that, again, is the world I lived in, system engineering, working with the Navy, the Marine Corps, and the Army and Missile Defense Agency on what are those requirements so that we're not trying to fit square pegs into round holes. And there's obviously the last thing from a system level is clutter requirements, right? If I'm in an urban environment versus a desert environment versus an open ocean environment, the environment that the radar operates in is a specific driver. Clutter is a big thing. I'll point out also operational availability, right? A truck goes out, comes back, and can get repaired. Airplane does the same thing. It flies in operation, it comes back to land. It has a different operational environment than, let's say, a strategic radar that's tasked with missile defense operations and has to stay online for 24/7. So that's another big operational consideration as we're kind of moving forward of what we're building and how it's going to operate, and then therefore going down to the packaging, what materials are required, what cooling systems are required to keep the things operational, how will it repaired, etc. So again, big picture, this is the 100,000 foot view of operational needs. It's all very interesting. From a radar business opportunities, this is kind of to highlight the big things that are going on, right? I think a lot of people have heard of the sensor program, which is the fact that by 2024, the government intends to vacate a portion of the L-band spectrum for commercial use, right? There's a big anticipation about what that means in terms of billions of dollars, and then the telecom companies all want to take advantage of that spectrum. So there's a bunch of radars that currently, I think there's 123 of them that operate in that L-band that need to be replaced in a different frequency band. Whether that's an S-band, a C-band, or an X-band, it's got to be vacated in order for the government to be able to sell that spectrum. So that program is a joint program between the FAA as the primary lead, because these are air traffic control radars. If you think about the ones you go to an airport, you see the orange spinners around the airport. Part of that is that replacement program. It's going to be the largest radar procurement in the United States. Okay, so that's coming up in shortly. There's a bunch of Army ground-based radar systems. Patriot, for example, is now, we've got the LTAMS procurement and things like that. They're basically in a modernization effort, right? Some of these systems have been fielded for 30 years. They've been ECP'd over time, but then they have a bunch of new procurements that are needed to expand their capabilities to keep pace of the threat and things like that. There's always tech insertions that you can do. Missile defense, you might have heard of the long-range discrimination radar, which is being built by Lockheed. It's up in Alaska. There's future LRDRs, you know, because if you know anything about the UEWR programs, those are old UHF radars that have been deployed since the early 60s. those types of systems need to be replaced in order to defend the country against a ballistic missile attack and those types of things. The Navy has an X-band procurement, and then I'm going to talk about science and technology. So here's all the systems on the right, again kind of highlighting the fact that some of these are in buildings, some are on ships, trucks, etc., different operational environments, different op tempos, and the like. A lot of radar business is one of the things that you could take away here to get in front of from a market. And then on the commercial side, there's radars for tankers and cruise ships, marine terminal support, and the like, as well as weather. And then there's this counter-UAS stuff that's going on, again, that you're reading in the news. Is it a federal acquisition through the Department of the Homeland Security, or is it a civil air defense kind of procurement that's going to happen? There was a market survey recently done by DHS on counter-UAS systems. There's a lot of systems out there. We counted 240 plus systems. We did a little market survey to see where we could put our technologies in there, but that's going to be a growing area and things like that. The characteristics, you know, for the most part in the commercial have been low cost and non-AESA for the most part, because really is an AESA an overkill for some of these applications that you need for open ocean kinds of things, you know, that type of stuff. So again, the commercial radar market. So there is the military and there is the commercial market. Again, a big focus for us and what I try to talk with our team as we're talking to our customers is really driving to the system requirements. You might have a packaging technique or a adhesive or a cooling method that your companies are providing, but basically, you know, it really comes down to you can't sell it if it doesn't meet the requirements, right? So in the DoD market, which I've spent my life, it starts with the system requirements review and it goes to the preliminary design and the critical design. It starts with some level of a top level requirements document or an SRD, a system requirements document that you really have to flow down. I see over and over again, I've been on winning teams and I've been on losing teams, and some of the losing teams is because I built them something that really didn't meet that specification and that operational, you know, need. So it really starts that way. So when I look at it, you know, it's going to be the big 5 things are the frequency spectrum, the power aperture gain equation, right? So an antenna basically has a sensitivity depending on how much power out the antenna puts out and also how big the antenna is, right? So because the receive is based on the aperture area, okay? So that's the power aperture gain study. So you can go big P and little aperture, make a smaller antenna with a higher power, go water cooled, right? You could go lower power, do an air cooled aperture, but do a bigger aperture and come up with the same sensitivity, right? That type of thing. So there's an equation there. How you do EDBF is elemental digital beamforming. So taking RF, go to digits and go to fiber, right? So you can take an aperture that has 4,000 elements and you can digitize every single one of them and be unaffordable, and that would generate a lot of heat with all of the A to Ds that you would need to do something like that. Or you can break it into sub-apertures and break it down and have less digitization, more elements digitized, and that type of thing. So elemental digital beamforming versus analog. And then I put 2 in italics and bold for this particular group because a lot of the things related to SWaP is space, weight, and power. That is how the radar fits on the platform, right? And what's the platform operational requirements. So when you think about the packaging, that's where a lot of the design decisions at the primes are being made relative to how am I going to cool it, how am I going to package it, am I using ceramic or not, you know, those types of things. It's the SWaP constraints on the platforms that often drive things, right? The power that a vehicle has to be able to power the radar may dictate whether you go to a higher power amplifier or a lower power amplifier and a bigger aperture, so those types of things. And then the environmental constraints, like I talked to, it drives you in a certain direction. I've also seen when I've had to tell suppliers you know, we thought we were going to use you, and then at the end of the day, when it came down to what the final spec was that the government gave us, they changed some of those environmental constraints, and no longer can we use that type of materials in our design because it doesn't meet those constraints. So getting in front of that. And I'll go through the acquisition process on the next 2 charts so you can kind of walk through that. Important point here is sometimes the government is very specific in what they need, and they don't give contractors trade space, so they really specify the system. I'm going to stay away from system names that have done things like that, but then there's others that really provide like a performance spec and leave everything up to the contractors to do trades on the technologies that they use. So there's 2 different ways that acquisition, and it's oftentimes it's somewhere in between those 2 things where they get very specific types of things. So again, the derived product development is a thing that really involves contractors doing analyses, system engineering, trades, and then deciding on what materials and what approaches to use. And then everything comes down to affordability. Affordability, the government does a lot of cost modeling, just so that you're aware, right? And so the systems have to be built to fit in those buckets. They do their best. We all do our best to fit into those buckets and keep the cost down. And then also, at the end of the day, what drives affordability is the competitions. You'll see a lot of announcements about the big guys all competing against each other on programs and then down selecting, and that's the government trying to initiate competition because competition breeds the affordability aspect. So keeping that in mind, when you're pricing your materials and your approaches, affordability is the key. Meeting the requirement, the threshold requirement, and then coming up with a pricing model that's supported. So I have a picture up here of the system family tree, kind of where MACOM stuff lives in the tiles. I'll get into that a little bit, but it goes across the basis. Next 2 charts, like I said, I'm going to talk about the acquisition process a little bit, and you know you're going to all have access to this. This is a chart I put together for a BD class that I taught. On things, I should say, and I should have said in the beginning, that all of the stuff that you see is for public release. So it's nothing that I took from anything that's controlled. And so that top graphic, many of you may have seen it, that is the government's acquisition process. I've tailored a little bit with the time frames across the top, the 1 to 2 years, the 2 years, 2 to 3, and the 30, etc. The bottom portion of this chart is really what I put together for the class to kind of describe the government line is what the government's doing, and the bottom line is what industry does. So whatever company I work for, this is what we should be doing as we're going through the different phases of the acquisition. So you can look at that as you guys are developing your approaches for things. So in the first phase, that material solutions analysis, you probably hear the term RFI, request for information, and you guys probably respond to, everybody here probably responds to request for information. The government does that market survey, right, of what's out there in the field that could meet my requirements. That's as they're working with the warfighters to figure out, what do I need? I need to see this target at this range, and it's got to have this quality of track, etc. So all of that is going on. And the other part is, in my next chart, I'm going to talk about contracted R&D and S&T dollars, where you can get those. There's also a lot of CRAD going on. So that's kind of the government line. Operational requirements, market survey stuff. Ends up in a milestone A, which really, that's the triangle on the top, which is when the government says, I'm going to build this ship, or I'm going to build this radar. I'm going to go forward, and they have a top level requirement. Then they spend a couple of years reducing risk through technology maturation and risk reduction, which is leading up to the preliminary design review, where you have things that are related to the preliminary design. And from a technology perspective, which a lot of you are geared towards, you are getting to a TRL 6, right? So you got to get through milestone B, which is a procurement milestone. You need to have your technologies up to a TRL 6, whether you're making devices, materials, etc. So that's kind of what the PDR is in the milestone B. And again, this is rough numbers. People want to know, why does it take 7 years to deploy a radar, right? This is rough numbers. Gator took 11 years to deploy from the time it was started to the time it just went through its LRIP milestone, and so on. So many of them take a long time to go through. The TD has some demos in it, then there's an engineering manufacturing development phase. So if you have like a 4-phase system, you might build a single phase and go through a bunch of testing. And then at milestone C, you're approved for LRIP, right? So there's a couple takeaways here for industry. One is nothing's guaranteed. A lot of times companies will think, I'm going to sell 22 systems, and they only end up selling 6 or whatever, right? Because of the fiscal constraints or, operational changes, because this does take so long. So when you're factoring in your business cases for your things that you're working towards, you've got to keep that in mind, that things are subject to change. It can also go the other way and buy more systems. And then also, a lot of things is these triangles are when the program can stop, right? So if you're selling into a prime, for example, and they don't pass the milestone B, they never get to convincing the government with their body of evidence that they're at TRL 6, the government can cancel that program or modify the program, which happens frequently. And the same thing at milestone C. They may produce an EMD. They've shown the capability of the system to the best of their ability, but it is not matured enough to be able to give them the government the confidence that it supports the warfighting modes. And then there's full rate production milestones and that kind of thing. So again, the way to use this chart is it's kind of what the government's doing on the top and where we in industry need to focus on to make sure we meet our things. And the one thing I'd say, like I'm just kind of looking at a bullet, I'll pick one. Opportunity assessment, right? Got to keep doing it all the way through the programs and things like that for your business case and that type of thing, because it's always changing. The other thing is risk assessments and things like that have to be done all the way through the program, the various phases of the program. So that's how you, and then the upper right, that modernization window. So we build things for the warfighters that last 30 years or more for the most part, right? If you look at all these systems out there, a ship, a submarine is supposed to be a 30-year ship and a submarine. We've had trouble having that happen all the time, but in some cases the platforms have been decommissioned earlier than the life cycle, but that is roughly the government plan. And so there's a lot of pieces and parts that can be constantly sold in there to be maintaining over 30 years of a life of a system. So note on the government investing in S&T dollars. So this is where we get into the advanced materials, right? So cracking those critical technologies. I've got the logos for all the services, because every service, Navy has Office of Naval Research, the Air Force has the Air Force Research Lab. All of these services, as well as organizations like DARPA and the Missile Defense Agency, all put out calls for technology demonstrations. So for those in here, or developments I should say, technology, core technology development and demonstrations, right? And the way that they do that, you guys probably, a lot of you know, but some may not, the Small Business Innovative Research grants and those postings that go out there. All the agencies have a constant broad agency announcement process that they go out there where they advertise, I'm looking for this group, this type of material, this type of a cooling system, this type of an approach to solving problems. So the BD staffs at all the major companies, we're just constantly churning and looking through these things to identify targets to where you can go and get government to help you develop and advance your product, whatever that product is. There's always the debate of the IP thing, right? So because if the government's paying to advance your technology, it owns parts of that IP. So you have to be cognizant that that is the case, that you will be looking into that. For each case is different, so it's on a case-by-case basis that we really need to look at it. And then I kind of skipped over what is S&T focused on. It's really focused on where are the gaps, right? So if you go on the DARPA website, they have the EIR initiative, the Electronics Resurgence Initiative. They have a few $100 million. This is, again, all advertised. If you go on there, they've got BAAs out there, right? They're looking for advancements in electronics. That was based on the fact that the government feels that there's a gap there today and where the United States industry base has been. So look at that capability. Similarly, I put a note, we should all look up Mantech. Mantech drives innovation for manufacturing. It's an all services group, so maybe some of you have Mantech programs that you're going through, but all of the DoD services have manufacturing technology insertion. So they're looking at better ways to do manufacturing technology and improvements. A little note on the TRL. I mentioned when you go across the life cycle of the program, here's the TRL levels. There's a handbook out there. There's a handbook for everything. You can Google it. There's one for manufacturing readiness and so on, and it defines where your technologies are. The big question for all of the large contractors is when they look at their systems, what parts and pieces don't meet a TRL level or a manufacturing readiness level. So you got to constantly reviewing that. But if you're trying to supply into a program, you should really do your own TRA analysis and kind of have a consultant come in and look at that and kind of walk you through the process so that somebody that's knowledgeable so that you know when you're proposing that you meet the TRL, the TRA requirements. Okay. I already mentioned sensor in the first chart, so this is in there. That's the operational view. Although the NOAA organization, this is an old chart, has fallen off of it, but again, self-proclaimed the largest U.S. domestic radar procurement going on in the United States, covering the continental United States. So getting now closer to the packaging and electronics, a little introduction, and this is the only chart that I have that's specific to a MACOM product, but I'll use this as an example. So MPAR, we built these MPAR panels. What you're looking at is a panel that is an 8x8 element S-band radar. So S-band radars for an active AESA to stay on grid, you know, for the radar pattern, it's 2-inch squares, so 2 inches between each radiating and receive element. And that's those dark squares on the panel. So going left to right, starting at the outside, that's a foam radiator with an aperture board, with a multi-layer aperture board. Then those things on the squares with what looks like fins on it, those fins are heat sinks because we're air cooled. And so each one of those squares is a TR module. So there's 64 of those TR modules with our HPAs, our transmit receive ICs on them. Those are all SMT mounted things. They fit into the back of the aperture board. We have a spacer board, which is just a mechanical fixture. And then there's a backplane PCB, which is where all the power control and FPGAs for all of the software interfaces to the panel for the system and the like are, you know, housed, if you will. So you put that all together and it makes a sandwich. It's about 23 pounds as it is with the back plane and the aperture board. So when you think about swap and things, space, weight, and power, weight, important, right? So if you did this in a 64 element traditional TR slat design, you'd have vertical TRMs slotted with a mechanical metal structure. This approach to that design significantly reduces weight in that area, so that's one of the things, as well as fat footprints. So space, weight, and power. The space part is what can I fit in it. So some of our customers are using this panel approach to fasten it to outsides of trucks, for example. Or you put 9 in a frame and you make an antenna out of it, and it's a fairly flat, planar plane. And then from a scalability perspective, the picture up at the right is called the MPAR ATD. We didn't do it, but MIT Lincoln Labs did 76 panels put together into a single face. So now I've gone from a 16-inch by 16-inch square with 64 elements to a full antenna radar with 4,864 elements, right, put together into, and that's the same size of a AMDR that Raytheon built or a spy radar that Lockheed built, those types of things. So scalability. So how that's a packaging method that MIT designed and worked with MACOM to build and design, and we are licensed to sell that as a product. Now our team basically has worked on various other configurations, C-band, X-band. So when you go up in frequency, you go down in size because the grid spacing shrinks, right? So an X-band 64 element antenna is only 5 inches by 5 inches, so your packaging challenges are much greater. Your ability to dissipate heat for the same watt at that frequency is much harder, right? So this is in the Empire configuration, an 8 watt. If I raise an S-band and I go up to, let's say, 20 watts or above per element, now I'm in a water-cooled configuration. And so that's those trades, right? Where this, you can blow air through it. If you went lower power, you could just do ambient cooling. You know, there's a bunch of different trades there from a cooling perspective. You get up above 20 watts, you start talking about water cooling, requiring a water cooler, a manifold to do chilled water going through the system and things like that. And then when you change frequencies, you also have the similar problems, right, as well as for those types of things, right? So that's kind of the electronic packaging. For thermal impacts of construction, we've highlighted some of the things. I've already talked a little bit about it. You know, working through the earlier chart, air cooling versus water cooling trades, the laminated boards considerations, standard vias versus embedded coins. So we're kind of doing those kinds of trades with suppliers and working through how we would do those different things. Plastic IC packaging and ceramic packaging, die attaches. So again, we've also done some analysis with various different types of materials for the heat sinks and things like that in the area as well. And then for us I mentioned we have a job right now where we're putting 9 panels into an array frame. So what is that array frame structure that we're using to hold the 9 tiles and the like? So that type of thing is thermal impacts and the construction of our arrays. MACOM, again, is a semiconductor company, and we primarily are selling TR modules, and the biggest thing is the 64 element tile. When we usually work with a customer for an aperture type thing, we're kind of expecting that customer to do the system engineering and the building of the aperture type approach. And then some of the other types of things on the programs and the way that the ATD is architected, the LRU, the lowest replaceable unit, the thing that you would replace when you want to fix it, is the 64 elements. So you get a 16 by 16 panel that you pull out with handles, and then basically you can take that back and we can replace the TRMs and then refurb it and send it back in there, that type of thing. So that's for logistics support and that types of things. And then we have assembly decisions that we've been walking through relative to the design. So when you think of some of the bigger radar procurements, and again, this is focused on that, you know, we're looking at various techniques for manufacturability. The sensor program to replace that many radars and the amount of electronics that are going to have to be manufactured, produced, and assembled is huge. And one of the risk items that the government has identified is how does the supply base support such a rollout of radar capabilities. So with that, that's all I have. This is my get off the stage chart. When you see the charts, I will have a set of acronyms in there in the background as well. So, and feel free to give me a call if anybody wants to talk about anything specific.
Thank you, Jerry.